Hey everyone, welcome back. Today we're going to tackle section 2.7 on the product rule and quotient rule. We have 4 learning objectives, 2 big ones and 2 little ones. The 2 big ones are this one right here, which is how to take the derivative of a product and how to take the derivative of a quotient. Through doing so, we're going to talk about higher order derivatives and more or less the notation that goes along with each derivative as you successfully take more and more derivatives. So you may recall when we were trying to figure out what the power rule was, we did a couple problems, I asked you to find a counterexample as to why this statement right here with the inequality or the not equal the not equal statement is true. In other words, why you can't just take the derivative of 2 different things individually and then multiply them together afterwards. We found that virtually with any normal function like x squared times x to the 4th, if you throw a coefficient out in there or whatever, you just don't get the same answer if you do a different order. So the question is, how do you handle a product like that? Today I am just going to give you the rule. I am not going to sit here and prove the rule in this video. If you'd like to see a proof of the product rule, you may do so. It's posted up on Schoology for you. There's about 1,000 videos on it on YouTube. It takes about 10 minutes to watch. If you're interested, go ahead and watch it. But what I'm going to do is I'm just going to give you the result of that proof, which is if you want to take the derivative of a product, then you're actually going to have to create 2 terms separated by a plus sign. And basically you're going to take the derivative of the first function times the original version of the second function. And then for the second term, you're going to swap that. So you're going to leave the first function alone and you're going to take the derivative of the second function. This is something worth committing to memory just because it'll make your life easier if you don't have to look it up over and over and over again. The quotient rule is even more complicated. There is another proof of it, again posted on Schoology. I think that the product rule is pretty easy to memorize just because it's like every combination that you would want. It kind of reminds me of foiling. So derivative of the first thing times the second thing plus the first thing left alone times the derivative of the second thing. The quotient rule is slightly more complicated. So if you are taking the derivative of a quotient, and again, if you can't get around it using power rule or something like that, then you are left with doing the quotient rule, which is a little bit more complicated. It's kind of like the product rule, except there's a minus sign in between. Okay, so that's one way to sort of kind of memorize it. The other way to memorize it is this little jingle down at the bottom, low d high, less high d low, denominator squared down below. And you'll see what that means is that I have the denominator, low d high, the derivative of the numerator, less high, so that's the numerator, d low, okay, so that's the derivative of the denominator, and then denominator squared down below. So we can see all that as a kind of a mnemonic. I think there's a jingle to go along with it, but I don't need you to sing in class or anything like that while you're doing it. You may if that floats your boat, but it's a little mnemonic to help you memorize exactly which term goes where and what you're taking the derivative of in each term. So even a relatively simple thing like x divided by sine of x, you're going to have to use the quotient rule to figure that out, and you're going to have to follow this rule to do so. So you list the denominator, and then you take the derivative of the numerator and you multiply those 2 together. Then you've got subtraction, and then you list the numerator unchanged times the derivative of the denominator, and then you take the denominator unchanged and square it, and that will get you the answer for the quotient. So obviously we're going to do a few examples today, and the first one as we kick things off is right here, and I'm going to kick things off with a little bit of new notation for you. This says, suppose s of t equals 3 times sine of t times cosine of t. So we have a product of 2 functions, and then we also have a constant out front. So we're actually going to use the derivative of a constant multiple and the product rule within a single problem. The other thing that this says is this new notation right here. This vertical bar, and then there's this thing that says x equals pi over 4. And what that means, basically, this means evaluate or such that. So when it says find s prime of t, evaluated at x equals pi over 4, or you can say find s of t such that x equals pi over 4. One way or another, basically what that notation means is substitute in a pi over 4 when you're all done. Let's see if I can undo all of these. There we go. All right. So our first job is to take a derivative. And then once we have that derivative, then we're going to evaluate it at pi over 4. So you'll notice this is a product. It's worth taking a shot. Can I get around this with power rule somehow? Since it's not really a polynomial, there's no exponents. No, we can't. So we are going to follow the rule. So if we want to go ahead and take the derivative of that, we kind of have to decide what is going to be our first function and what's going to be our second function. So it doesn't really matter how we break this down, but let's include the 3 with the sine of t, and we'll break down the cosine of t all separate by itself. So I'm going to consider f of t to be that first chunk and g of t to be the other chunk. So that means that s of t is going to equal the derivative, and you can do it in any order. You notice that the product rule was ultimately a sum. So as long as you take the derivative of the first item and then leave the second item alone, and then vice versa in your other term, all is good. Okay, so I'm going to take the derivative of the first thing. So I'm going to go 3 cosine of t. So that's the derivative of 3 times sine t. And then I'm going to leave the second thing alone. Then I'm going to introduce that plus sign. Then I'm going to leave the first function alone. That's 3 sine t. And then I'm going to take the derivative of the second item, which will be a negative sine of t. Then we just do a little bit of work here. So we're going to have 3 cosine squared of t minus 3 sine squared of t. If you wanted to, you could factor out a 3. It gets tantalizingly close to a Pythagorean identity, but alas, there is a subtraction symbol in the middle instead of a plus sign in the middle. Remember that sine squared plus cosine squared is 1. So we're not quite there. This is all it is. That's about as far as you can go. And both with the product rule and the quotient rule, there's always a debate of whether, how much do you want to simplify. I'm not sure I have a super strong opinion on that unless the problem itself says show that the derivative of this product is something specific. And then you got to bring it all the way to that something specific. But other than that, I think you're okay leaving some things hanging. As long as you can evaluate the derivative, because that is our job here, we have to evaluate this at x equals pi over 4. So I can actually use that bar right here to tell the reader that I'm going to go do that right now. So, or I could just say s prime of pi over 4 equals, and then we sub in our thing. So we're going to say cosine of pi over 4, and then we're going to square that, and then we are going to, I'm going to put the 3 in front of each term. I'm going to distribute the 3, even though I just factored it. And then sine of pi over 4, and we're going to square that. So it looks like we are going to have probably 0 here. 3 times square root of 2 over 2 squared minus 3, and that is also square root of 2 over 2 squared. So we have plus and minus of the same term. Well, what do you know? That derivative is 0. S prime of pi over 4 is 0. Well, there we go. We've evaluated a fairly complicated derivative at a point. If we were to write an equation for a tangent line or something like that, we would have a slope of 0 on that thing. A little weird, but that's all right. Next example, we have another product. So I'm still in a product rule, and I'm again introducing you to some new notation. You'll see this f of 4 thing. So what that stands for is the fourth derivative. Notice that the problem says find the fourth derivative of f, and then it says evaluate the fourth derivative of f at 1. So that little 4 stands for the fourth derivative. What happens as you take derivatives, so let's just say we have our original function. We go through this progression of f, and then we go f prime, and then we go f double prime of x. And at this point, you might see some books go f triple prime of x, but you also might see some books do this, and it means the same thing. Take the third derivative, or the third derivative of f, and in this case, instead of writing 4 tallies or maybe 7 tallies, however many derivatives you're taking, you're just going to do a little superscript up in parentheses, whatever derivative you're taking, in this case the fourth one, and that's going to represent what you need there. Okay, so just a little notation. If you are asked to take like the 8th derivative of something, just know that that's how they're probably going to phrase it rather than with 8 different apostrophes as you go along. So let's get to work here. Let's take the 4th derivative of x times e to the x. So this might be a little work. I have to take a derivative of a derivative of a derivative of a derivative. So let's get started. Let's do f prime of x. We have to use the product rule. So I'm going to take the derivative of the first thing to start it off, times the second thing unchanged, plus the first thing unchanged times the derivative, and the derivative of e to the x is itself. So we get something like that. Notice that both terms have an e to the x in it, so I think if we factor that out, I think we might get a slightly less complicated version of itself. So we got 1 plus x there. So I've got f prime of x equals that. And then we can, to do f double prime, we could just keep on applying the product rule. So in this case, I'm going to take the derivative of the first thing, which is now e to the x, the way I've written it, times the second thing unchanged, all right, plus leave the first thing unchanged and then take the derivative of the second thing. So that means that we've got another thing where we've got, well, let's see, there's an e on everything, right? So that basically means that we've got e to the x, and there will be a 2 plus x, because there'd be 2 1s left over if I factored out an e out of everything. Okay, so it looks like we're establishing a pattern here. So we had f double prime equals this, and it's just 2 plus x. That's 1 plus x. I imagine, if we do f triple prime, so if we work on f triple prime, we run through the same thing. Derivative of e to the x is e to the x. Leave the second thing unchanged, 2 plus x. And then we do the plus sign. Then we leave e to the x alone, and we take the derivative of this polynomial. The derivative of the constant goes away. The derivative of x is 1. So we have times 1 again. And you can see that if I factor in e to the x out of everything there, I'm just going to get left over with one more 1 there. So it's going to be 3 plus x. I imagine that that same pattern is going to happen with the 4th derivative. So I think I'm fairly confident in just writing this down, that the 4th derivative of x e to the x is 4 plus x in the parentheses and then times e to the x. And you could list the e to the x in either place. Okay, so there's the 4th derivative. I did drop my parentheses of x. Don't want to do that. Let's put those back there. All right, then I'm happy. And if I would like to evaluate the 4th derivative of f, so f 4th derivative at 1, then I would be going 4 plus 1 times e to the 1, which would equal 5e, just like that. So that's ultimately the answer that we wanted right there. We also found the 4th derivative on our way there. Let's move on to the next example. All right, this one's a little bit more conceptual, and there's definitely an AP style vibe to this sort of question. It says, suppose f of x is equal to the square root of x times g of x. And then it gives you some kind of like tabular data. I would basically some data points that you might find in a table of values. It doesn't give you the table, but it gives you some values that are possibly in the table. It would like you to find the derivative of f evaluated at 4. Well, that means that we're going to have to find the derivative of that thing. So f prime of x, I'm going to do the product rule. So I'm going to take the derivative of the first thing. Hopefully you have this memorized. 1 over 2 times square root of x. Leave the second thing alone. All right. And then plus. And then we're going to leave the first thing alone. And then we are going to take the derivative of the second thing. Now, I don't know what g is, but the derivative of it is g prime of x. All right, and then all we have to do is put a 4 in there, and hopefully they have provided us with enough information to fill everything out. So if an x is 4, then I have 1 over 2 times the square root of 4 times g of 4, which they said in the problem was 2, plus the square root of 4 times g prime of 4, which they said, instead of writing that, I am going to write a 3. And look at that, I have all numbers. So let's see what we got here. We got 1 over 4 times 2 plus 2 times 3 is 6. So we've got 1/2 plus 6 6.5. Bam. There we go. Let's move on to the next one. Look at that. We've got a quotient finally. All right. So the quotient rule. We haven't seen that one in a while. So let's just refresh ourselves. Here's the quotient rule. Low d high less high d low. Denominator squared down below. Okay. Let's give that a shot. We've got a simple polynomial here. We should be okay just to go ahead and get it done. Okay. So we're going to go low d high. So the derivative of the high. So I'm going to bring down that power out front, negative 24x to the 7th, less high d low. And then we've got 4x to the 3rd minus, well, minus 5 would go away, wouldn't it? So we don't even have to list that. So the derivative of a constant is 0, so we leave that alone. And then we list the denominator unchanged and squared. All right, so then you have this situation where you're like, how much do I simplify here? And sometimes you're told to show that the derivative of a function is a certain thing, and then you are forced into a situation where you need to go figure that out. However, on most problems, at the worst, you may have to recognize a slightly different form of this in a multiple choice bank, but most of the time you're going to be asked to evaluate this at like 0 or 1 or 2 or something like that. And frankly, in that form right there, it's a little messy, but you could plug in a 1, 2, 3, or 4 or a 0 pretty easily and get yourself a workable answer. So I would advocate for maybe just leaving it like that. That's an answer. That's fine. It's an ugly answer, but it is an answer. Again, occasionally you might be tempted to take it a little further just because, you know, things simplify and it's pretty nice. Okay. And that's kind of the case right here. Now that we have the ability to take the derivative of a quotient, we can also play around with the reciprocal trig functions a little bit, okay? So if you remember, this would be the same thing as taking cosine of x over sine of x. So we can express that as a quotient, and we can use quotient rule. So let's give it a shot. Low d high, so sine of x, low, d high, times negative sine of x. So I'm taking the derivative of cosine there. Subtract high, d low, cosine x, d low. That would be another cosine of x. Draw a line down below, denominator squared. All right, so we're going to go sine squared of x. I'm going to put a little squared there. All right, so it looks like, let's see, I can pull a negative out of the top. And then I have sine squared of x, because I have sine times sine. And if I pull that negative out, I've got a plus sign, cosine squared of x, over sine squared of x. And then a little alarm bell should go off right here, because you should notice that you have a sine squared plus a cosine squared right there, and that is 1. So we can make this thing pretty darn simple. So this is one where you definitely don't want to leave it in its intermediate form right there, because we can do an awful lot to this one. So we got a negative 1 over sine squared of x, and if we wanted to write that down a little bit nicer, that is a negative cosecant squared of x. As you might suspect, it's going to be nice to be able to do that in one step. So at this point, one of the problems on your worksheet today is going to just straight up memorize or make sure you have memorized the derivatives of all the basic 6 trig functions: sine, cosine, cotangent, tangent, secant, and cosecant. You will be asked to find the derivatives of some of those spread out over the homework, practice test, and test. But for now, it's handy if you just straight up have them memorized. There's 1 out of the 6, and I think you've got sine and cosine memorized already, so you got half of them done. Okay, let's move on. Let's do this one right here. I think this is our last one for the day. So again, we have a quotient. You might be tempted to split that denominator. Remember, you cannot split a denominator. You can only split a numerator. So take time to recognize when you can use that power rule and when you cannot. This is a situation in which we cannot. So let's write out an expression for g prime of x. We're going to go low d high less high d low. So we're going to go low 1 plus x squared d high. So that's e to the x, less high, d low. E to the x times the derivative of 1 plus x. Derivative of 1 is 0, and then the derivative of x squared is 2x. So we'll put that there. Draw a line down below, denominator squared. 1 plus x squared, and we have to square that quantity. And I mean, we could factor in e to the x out, but what we are asked to do is write an equation for a tangent line at x equals 1. So really all we need to do is sub in a 1 here and get a value. So let's see if we can work on that a little bit. We got g prime of 1 equals, I suppose that would be 2e to the first minus e to the first times 2. All right. Well, I suppose that's 0. Look at that. All right, let's just make sure it's not 0 over 0. 1 plus 1 squared. So that would be a 4 on the bottom, so I think we're safe. So that's safe to say that's 0. Fantastic. Okay, so we need a tangent line. So my slope for my tangent line is 0 apparently, so that really just means we need to know the height of the original function. So we need to know g of 1 in order for that to work. So g of 1 is e to the first, and then we have 1 plus 1 squared. So that would be e over 2. So I bet if we wrote an equation, we got y equals m times x minus x1 minus y1, well, we just figured out that this is 0, so it wipes out everything that follows there. That's plus sign, sorry. And then plus, we just figured out that was e over 2. So it looks like we're drawing a horizontal line, which makes sense. A horizontal line has a slope of 0 at e over 2. And in fact, that is correct. I've taken the liberty of drawing those two things out, and you can see that the function g of x, which is here in blue, has a horizontal tangent line. Doesn't have a minimum or a maximum, and that's kind of cool. It just has a horizontal tangent line at a value of 1. That's all I have for you today. I'll see you next time.